of you. So today we are going to have a very brief session on the concept of work done in thermodynamics. So only we will discuss the concept of work done. We are not going to discuss anything else. So you are aware that there is a system. Okay, suppose this is a system. It could be an ideal gas, it could be anything else. So the system has got a volume of V1 and it is subjected to external pressure PEX, and due to this external pressure the volume goes down from V1 to V2. So earlier the volume was V1, now it goes to V2. So you know that the work done during the transition from V1 to V2 is minus PEX into V2 minus V1. Okay, this is a basic formula of thermodynamics which we all know. Now why is the minus sign there? The minus sign is there because so why is there a minus sign over here in the front? Why is the minus sign there? Because when the system is getting compressed, so compression means that compression means that work is done on the system, and expansion means work is done by the system. So when the system is getting compressed, so volume is going down from V1 to V2, so it is getting compressed. So that means work is done on the system, that is considered as positive, that is a convention. If the opposite were to happen, it was expanding, then work is done by the system, that is considered negative. This sign convention is very important, and you know very well why it is all the more important, because it is the opposite of the physics sign convention. So compression means work done on the system, and that is positive. Expansion means work done by the system, that is negative. So the minus sign takes care of that. So if you have a minus sign and if it is compression, automatically the answer will come positive. And if it is expansion, this will automatically give you an answer negative. Automatically it will happen. But this is only if PEX is constant. If the external pressure is constant. External pressure constant has got a name. It is called isobaric process, right? If the external pressure is constant, what is that process called? Isobaric process. So if the external pressure is constant, then this is the formula. Suppose the external pressure is not constant, then you have to write dW equal to minus PEX into dV. If the external pressure is constant, then this formula works. If the external pressure is not constant, then you have to take it in increments. dW is minus PEX into dV, in which case W will be integral V1 to V2 minus PEX into dV, right? And needless to say, the equivalent situation in terms of graph will be the area of this portion. So the situation corresponding to this calculation will be the area under this graph from V1 to V2, right? Okay, now there are two extreme things you have to remember. One is the process is happening very slowly, then it is called reversible. Okay, and if the process is happening very quickly, see, if the process is happening very slowly, infinitely slowly, that process is called reversible. If the process is happening at a finite speed, like not infinitely slowly, finite speed, then it is called irreversible, right? Now the thing is that Just remember one thing, that if the process is happening infinitely slowly, then the work done on the system is the least, right? In order to take the system from volume V1 to V2, if you conduct the process infinitely slowly, then work done will be the least. It's a rule. Okay? If the process takes place at finite speed, so anything other than infinitely slowly is called irreversible. It's as simple as that. Okay? And if it is reversible, then the work done on the system will be the least, right? Now, infinitely slowly, why is it called reversible? The reason is that while the piston is going down, the external pressure and the pressure inside, like the pressure inside is PIN. So this external pressure and internal pressure, they are related by this expression. External pressure is internal pressure plus dP. External pressure is internal pressure plus dP. This is the relation. Okay? And suppose if you just change this plus dP to minus dP, then the external pressure is infinitely small quantity less than internal pressure. So that is why it is called reversible. Because when this is the equation, that means the piston is going down. But when this is the equation, that means the piston is going up. So by changing plus to minus, the movement of the piston changes. So that is why it is called reversible. Right? Now, if it is a reversible process, then this formula V1 to V2 so V1 to V2 minus of, instead of PEX you write PIN plus minus dP, so minus of PIN plus minus dP into dV. So this will be, now PIN is the pressure of this gas, like I said, so that will be nRT by V. Okay, so PIN is the pressure of this gas, that will be nRT by V. Now let us say that the process is isothermal. So it is reversible and it is also isothermal. Then what will happen? T will become constant. So it will become minus 2.303 nRT log V2 by V1 to the base 10. Actually, when you integrate dV by V, the answer will come log base E, but log base E is not very comfortable. We prefer to use log base 10. Okay. So if isothermal reversible, minus 2.303 nRT log V2 by V1 to the base 10. Okay. So this is the formula in case of isothermal reversible. Right. Now, apart from the fact that for isobaric, this is the formula, number one. Number two, so for isobaric, this is the formula. Number two, this one, and this graph, this is the general formula. And number three, for isothermal reversible, this is the formula. What other formulas are there? So, if work is done against free expansion, that means that the system is expanding against vacuum. Suppose there is a free expansion, that means the system is expanding, but over here there is vacuum. So PEX is 0. So for free expansion, the work done will be 0 because PEX is 0. Secondly, isochoric. Isochoric means there is no change in volume. So the work done will again be 0. Then we come to adiabatic. Okay, now one thing I want to clarify that in these two formulas, that is isothermal, reversible and adiabatic, I am assuming ideal gas. Okay, in these two formulas, I am assuming that the system is an ideal gas. Like this is a general formula, there is nothing about ideal gas over here. This one, general formula, but isothermal, reversible, this formula is assuming that the system is an ideal gas. Adiabatic, assuming that the system is an ideal gas. So assuming that the system is an ideal gas, we get the formula of isothermal reversible, we get the formula of adiabatic. Okay, right. Now the thing is that most of the time we are doing chemistry, thermodynamics, you have to remember, most of the time in the laboratory we are doing some experiment, it is in a test tube or in a beaker. So in laboratory conditions the pressure means atmospheric pressure, and suppose you are doing some experiment, so while you are doing the experiment the pressure will be constant only, right? While the experiment is going on, the pressure will be atmospheric pressure, which is constant. So virtually you can say that PEX into V2 minus V1, it works for chemistry all the time. In fact, there is a separate consideration for this, that is enthalpy, where pressure is assumed to be constant. We'll come to that in the next session. We won't discuss enthalpy today. So this PEX minus PEX into V2 minus V1, this formula works for chemistry virtually all the time, because in laboratory conditions the external pressure is constant. So what we can do is, we can have a discussion like this. So laboratory conditions, PEX is constant. So in laboratory conditions, PEX is constant. So what we can do is that we can have a discussion something like this. Suppose if I tell you that you are performing a reaction in laboratory conditions, PEX is constant, and if I tell you that it is also isothermal, okay. So then you can do one thing, instead of V2 you can write nRT by P2, instead of V1 you can write nRT by P1, right? You are doing laboratory condition and it is also isothermal, then instead of this you can also write this. That is number one. Number two, suppose let us say that I am doing a reaction like this. Suppose I am doing a reaction like this, Fe plus H2SO4 is FeSO4 plus H2. Suppose I am doing this reaction, Fe plus H2SO4 is FeSO4 plus H2. So for this reaction, what will happen is, there are two possibilities. Suppose if I perform this reaction in an open beaker, suppose Fe plus H2SO4 is FeSO4 plus H2. Suppose I perform this reaction in an open beaker. So in an open beaker, what will happen? W will be minus PEX into nRT by PEX minus 0. So if I am performing this reaction in an open beaker, W will be minus PEX into nRT by PEX minus 0. Why? Because it's an open beaker, so the gas will come out and it will be at the atmospheric pressure only, and initial volume will be 0. And suppose if I do this reaction in a closed container, then initial volume, final volume both will be 0, so work done will be 0. So this is another example of how to use this formula for laboratory conditions, right? Okay. Okay. The other thing is, suppose I have a situation where there is a change of state. So I am discussing only the laboratory conditions now. Suppose there is a change of state. So change of state means suppose ice is melting to water. So at atmospheric pressure. So minus P external, and then V2 I will write mass by density of ice, mass by density of water, minus V1 will be mass by density of ice. So this is another usage of this formula, Pex into V2 minus V1. So if ice is changing to water, then mass by D2, D2 means density of water, minus mass by D1, D1 is density of ice. So that completes all the concepts related to work done. Okay, work done is minus Pex, V2 minus V1 is for isobaric, right? These three are the general results. Infinitely slowly is called reversible. Work done on the system is the least. And finite speed is irreversible. Pex is Pin plus dp, and Pex is Pin minus dp, that is why it is called reversible. And for reversible, if you take this integration, and for an ideal gas it works out to this. If it is isothermal, this is the work done. Free expansion, work done 0, isoporic, work done 0, adiabatic, work done, this is the formula. The formula minus Px into V2 minus V1 is for laboratory conditions. Px is constant always. So we can rewrite V2 and V1 like this if it is isothermal. If you have a very specific reaction like Fe plus H2SO4 is FeSO4 plus H2, then you can use this formula in multiple ways. If this reaction happens in a closed chamber, because these two are not gases, so initial volume will be negligible, so 0, and final volume if it is closed chamber will be 0, so work done 0. If it is an open chamber, then H2 will be at atmospheric pressure because it is open, so the final volume will be nRT by P external. So this is the usage, and for change of state we can use this formula. So this is the total details of the work done, and now let's have a few homework questions based on work done. Okay, the first question is that 8 grams of oxygen at STP is expanded to double the volume. 8 grams of oxygen at STP is expanded to double the volume. What is the work done? Options are 22.4 liter atmosphere, 11.2 liter atmosphere, 5.6 liter atmosphere, minus 5.6 liter atmosphere. This is question number 1. Question number 2, density of water is 0.915 gram per cc, density of ice is 0.915 gram per cc, density of water is 1 gram per cc. So what is the work done if 1 mole of ice is converted to water at 1 bar? Options are 0.167 joule, minus 0.167 joule, 0 joule, minus 1.67 joule. This is question number 2. Question number 3. 5 moles of an ideal gas at 27 degrees Celsius is isothermally expanded from 10 atm pressure to 4 atm pressure, keeping external pressure at 1 atm. What is the work done? 5 moles of an ideal gas at 27 degree is isothermally expanded from 10 atm to 4 atm at external pressure 1 atm. What is the work done? And the options are minus 1870.6 joule, 1870.6 joule, minus 18.47 joule, and plus 18.47 joule. So this is question number 3. Question number 4. There is an ideal gas, it expands from 10 to the power minus 3 meter cube to 10 to the power minus 2 meter cube at 300 Kelvin, and external pressure is 10 to the power 5 Newton per meter square. So what is the work done? Options are minus 900 joule, minus 900 kilojoule, 270 kilojoule and 900 kilojoule. This is question number 4. Okay, so these are the 4 homework questions based on today's thermodynamics sessions. I am giving 4 questions today instead of 5. So 1, 2, 3 and 4. So just do these homework questions and submit it by 9 p.m. tomorrow, and if you want to verify if your homework is correct or not, then you can join the meeting at 9 p.m. I'll tell you if your homework answers are correct. Okay, thanks a lot all of you. I'll end this session. Thank you. Bye all of you.